Hi everyone and welcome to this new video about three-phase power circuits. That is our example number 4, and in this example we will consider the final configuration of delta system. So we have a delta connected source and we have a delta connected load. Now for this system we have the following data. The phase voltages are 200 volts with a phase orientation of 0 degrees for VA. And VB and VC exact same amplitude, but the phases are 120 degrees and minus 120 degrees, actually as shown here. The loads are ZA, ZB and ZC, all exact the same. And the values of those loads are 20 with a phase of 40 degrees, so 20 ohms with a phase orientation of 40 degrees. So we have actually an inductive load. The following we would like to calculate the line voltages, the load voltages, the load current, line currents, and the phase currents. Okay, let's start with the first one, which are the line voltages. In this case, the load is already given in the rectangular representation, so we don't have to do that as we did in the previous example. So let's first look at the VL1 and VL2 and VL3. So what we have actually looking at the circuit VL1, which recognizes VL1 is this one for point A to point C. What we did always was we would turn in the clockwise direction, so that's now actually our sequence. So as you can see, from point A to point C, that's VL1, but that is exactly the same as VA. So, and VA is given. So again, this is not so difficult. It's actually 200 phase of 0 degrees. Now let's move on for VL to VL2, which is this one, from point B to point A, again in the clockwise direction, which is exactly the same as VB. So again, we can say VB, which is equal to 200 volts, the phase of 120 degrees. And the last one, VL3, which is this voltage from this point, from B to that. Now, if you want to go, of course, in the clockwise direction, it will be from point C. This one is exactly the same as point C to point B, which is exactly as VL3. But that is also VC, and VC we already know, which is given in the example, which is 200 volts phase of minus 120 degrees. Now those are the three unknowns for question A. So that's actually pretty straightforward and very easy done. So let's move on to load voltages. And load voltages are the voltage across each load. So what we want is, what is the voltage V? So let me make this clear. What is actually the voltage? For example, for A, I would like to know what is the voltage here. So V of ZA. And I can do the exact same for VZ of C and VZ of B. So I won't write it down, otherwise it will be cluttered. So let's move on for VZ of A. And that is exactly, again, what you can see is this point, from that point, from this to that, from left to right, is exactly the same as from A to C. Again, we have VA. So again, for this configuration, it's pretty straightforward and really easy to calculate the unknowns, and it's exactly the same as 200 phase 0 degrees orientation. And if you look now for the ZB, for voltage across ZB, that will be, of course, exact same as VB, which is 200 volts and 120 degrees phase orientation. The last one, VZ of C, which will be V of C. If you look at carefully, it is from this point to that point, which is exactly from point C to point B. Again, in the opposite direction. And this will be, again, 200 volts with minus 120 degrees. Now, that's also done. It goes very fast, so we have to for question A and B we have already calculated. Now look at the question C, load currents. Now those are also not so difficult because we already know the voltages across these elements, loads, and we know also the expression for the impedances. So we can use Ohm's law. So what we can do is load currents. So what we can say is the IL, or expressed in a different way, IZA. So IZA will be VZ of A divided by ZA, which is 200 divided by 200 phase 0 degrees divided by 20 phase of 40 degrees. So if you do the math, you will get 10 phase of minus 40 degrees, and this will be in amperes. Okay, now if you do the same for the current IZ of B, which is a load current of impedance ZB, which will be again the associated voltage across the impedance divided by its value. Again, all of the impedances are exactly the same, so we have a balanced system because the load are exactly the same and the source are exactly the same, so we have a complete balanced system. Okay, let's fill in the values. We have the voltage and the impedance, then we have again 10 amperes, but the phase is in this case plus 80 degrees. If I now calculate also the EZ of C, which is VZ of C divided by ZC, which is 200 volts phase minus 120 degrees divided by 20 phase 40 degrees, and this will be 10 volts with a phase of minus 160 degrees. And this is actually for the load currents. Now we have actually done very easily and very fast the A, B and the C questions. So let's move on to question D, and that's actually the line current. So it's actually those currents IL1, IL2 and IL3. Okay, for that we can of course use a circuit and use the Kirchhoff current law. So what is IL1? IL1 is this current, and it is actually produced by IZA minus IZB. So if you use the Kirchhoff current law at this point, you will get IL1 is IZA minus IB. And we know these two because we already calculated that in the question C. So what we can do is the following. So let's make the type clear. So line currents. So I will require IL1, which is IZA minus IZB. And we know the expressions, so let's write it down. 10 amperes minus 40 degrees minus, again, 10 amperes, but it will be plus 80 degrees. And we have done this many times to convert the polar expression into rectangular such that we can add, because the addition and subtraction is easily done if you have their expression in the rectangular form. And that's actually what we always did. So if you want to follow the exact details, I would like to refer you to the videos in example number 1 and 2 and 3. I have done that in great detail, and you can also look at the separate video about phases and complex numbers. So I will leave the details out and I will give the result as 10 times square root of 3 times minus 70 degrees. That's actually the calculation and the result for IL1. What you observe is the following. The amplitude of the current, for each current is actually 10 for the load currents, is multiplied by square root of 3. And this current, the first one, has to reduce by 30 degrees. So you will actually do minus 40, minus 30, and you will get minus 70. So that's actually interesting to note. So if I want to do IL2, which is if you move up again in the circuit, what you see is IL2, which is this one, which is IZB minus IZC. So I have IZB minus IZC. So IZ of B minus IZ of C. And of course we already know this. IZ of B is 10 amperes with a phase of 80 degrees. And we have also the phase for the value for IZC, which is 10 amperes and a minus 160 degrees. Again, if you do the math, going from the polar representation to the rectangular representation and then simplify and then again transform back to the polar expression, you will get the following: 10 times square root of 3, again the same amplitude, and the phase will be 50 degrees. So what you observe is the following. So we see some pattern. This will be, amplitude will be multiplied by square root of 3, exactly the same, and this first phase, which is minus 40 in this case, will be subtracted or will be reduced by 30 degrees. And it's actually exact same done here for the 80 degrees. So we are 80 degrees minus 30 degrees, and we end up at 50 degrees. So if I do that also for IL3, which is the expression for IZC minus IZA, if you look at the circuit again, so IL3, which is this one, so will be IZC minus IZA. So just using again Kirchhoff current law at this point, so we have determined the IL3. Again, if I now substitute the values, I will have 10 amperes minus 160 degrees minus 10 amperes and a phase of minus 40 degrees. Again, you can do again the math by converting the polar notation to rectangular form, or you can see the pattern and use that. So what I can say is that it's 10 times square root of 3 for sure for the amplitude, and this phase must be reduced by 30 degrees. So I will end up at minus 190. So I will have minus 190 degrees. And these are the line currents. So we're already done with question D, which is very quite easily done. So let's move on to the last one, which is the phase currents. So what are the phase currents? So let me make that also clear. Let me use the red color. So the phase current for each source is, for example, for VA is IP of A, which is flowing in this direction. This is the supplied phase current. For the VB is IP of B, and for the C is IP of C. And these are the currents we would like to determine. Again, you can do the math. For example, if you do the Kirchhoff current law at this point, it will be IL1 is IPA is equal to IL1 minus this one. But you know both of them, you don't know both of them, so it will be a complicated equation to solve it. So there's also a formula for this. So, and we can again check that. So the formula is the following. So let's move to question A, phase current. So I P of A is equal to the line current, the first one, IL1, because you are looking at the first phase voltage. So IP of A is IL1. You divide that by square root of 3. So that's actually the amplitude, the value of the IL1, which is this one. You divide it by square root of 3. And you look at the phase of the IL1. I will denote it as theta sub L1. And you add 30 degrees. That's actually the formula. So you will have the following. That is 10 square root of 3 divided by square root of 3. And the phase will be minus 70 plus 30. And you will have 10 phase minus 40 degrees in amperes. And what do you recognize? This is exactly the same expression for the load currents. So the load currents are exactly the same as the phase currents. So this is, let me do that in red. So this is exactly as IZ of A. That's interesting. So I can use the same formula for the phase current for source B. So IP of B will be IL2 divided by square root of 3. And again, in the phase of theta, L of 2 plus, again, 30 degrees. And I will look at the expression for the IL2, which is shown here. Again, the same amplitude, but the phase is 50 degrees. So if I substitute all those values in my equation, I will have the following. So the 50 degrees plus 30 degrees will result in 10 phase 80. And again, what do we observe here? This is the load current IZ of B. So we end up again in the load current using the phase current. So the phase current C, which is the last one, will be IL3 divided by the square root of 3, that's just a factor, and then theta of IL3, so it is theta sub L3, plus again 30 degrees, and you will have 1 of 10 times square root of 3 divided by square root of 3. Phase, what we had was minus 190 plus 30 degrees will be 10 phase minus 160. And again, what you observe is this was also IZ of C. So we have exactly the same expressions for the load currents and for the phase currents. So the phase currents for this configuration, delta source, delta load, will be exactly equal to each other. So if you can see, it's IZA. I will a bit zoom out so you can see in full picture what we have. So IZA was this, exact same for the phase A. IZB was this one, it is the exact same as phase B. And for phase C we have this one, which is shown here. So that's actually for question, for example number 4. And that concludes actually the whole set for the power systems or 3-phase power circuits for Y connection and then Y delta connection. That was example number 2. And for delta Y connection, that was example number 3. And this one, the final example, example number 4, considered the delta delta connection. Of course, we will move on with different subtopics, and I will come up also with design examples and other interesting issues. So don't forget to like and share the video and subscribe. So I will see you next time, and if you have any suggestions, comments, or any mistakes you have seen, please place it in the comment section. I will try to answer them as soon as possible. Thank you very much, and I'll see you next time.